today. So here I call it self-cleaning flock filter settler. But whatever that flock filter settler is, think of that as temporary words, and maybe you will help me figure out what we should actually call this. So if I want to put this in context, where does this fit? And so we'll begin with a discussion of where sedimentation fits in a traditional conventional water treatment plant design, and then what it looks like in an agua clara design. And then we're going to talk about various pieces. We'll talk about the whole unit as one, the flock filter SED, and we'll look at some pictures of plants, both schematics and also plants under construction. Then we'll delve into the flock filter. We'll talk about how the flocks are resuspended. We'll talk about flock hoppers, and then we'll talk about what's happening at the top of the sedimentation tank, which is actually where sedimentation is happening. So we'll talk about capture velocity and in the context of plate settlers, and we'll talk about a crazy phenomena called flock roll-up. So that's what's coming over the next 2 weeks, 4 lectures. So here's a conventional water treatment plant. You take a raw water, a surface water, a creek, a stream, a river, a lake, and you run it through an entrance tank where you screen it, remove grit, and you measure the flow, get rid of any sludge that comes out of that, any grit. You add a coagulant in a mechanical rapid mix. Then you go to a mechanical flocculator. Then you go to a sedimentation tank where sludge is removed, and often there's a mechanical system for scraping the sludge out of the bottom of the sedimentation tank. And you go to a rapid sand filter, usually a dual media filter where there's anthracite and sand. And then there's backwash water that comes out of that. And you go on to disinfection and to storage and to distribution. Okay, so that's the whole picture again, to remind you where we're at in this story. And the piece that we're focusing on is sedimentation. However, in an agua clara plant, it looks a little bit different. So here's an agua clara plant. We bring raw water in, we do the same things in the entrance tank. And then we currently don't think that rapid mix has any significant role, and so we're not including it in our design, and we're going straight to hydraulic flocculation instead of mechanical flocculation. And you are now becoming experts on hydraulic flocculation. And then there's a new process, which we're calling a flock filter. It's in the literature, it would be referred to as a flock blanket. And I have rebelled against that term ever since I first heard it, because it is not cozy. You cannot use it to wrap yourself up and keep warm. And it doesn't look like a blanket. And so it's not clear why the term blanket was added to that. And so now that we, as of about a year ago, have a much better idea of what the physics is, of what's going on inside that system, we're going to call it a flock filter. That's in the bottom of this sedimentation tank that we're going to be studying. Then there's 2 places where the water goes from that flock filter. It either goes to a flock hopper where the sludge is discharged from, or it goes up to the plate settlers, and out of the top of the plate settlers is where the clean water goes. That goes on to a stacked rapid sand filter that has backwash water as well, just like a conventional filter, and then storage and distribution. So the very end of the system looks identical again. So we're in this middle part now where instead of just a sedimentation tank, there's a flock filter, there's a flock hopper, and there's plate settlers. And we're going to figure out how those things work. So this is a side view of this system. And I want you to slowly begin to learn how water flows through this system, because you have to understand how water flows through the system and how particles flow through the system, so that you can begin to understand how all these pieces fit together. So the blue dots are my pretend water molecules. They're humongous water molecules that are in the inlet channel. That inlet channel has flocculated water that just came out of the flocculator, okay? And that inlet channel flows across these pipes, and so the water can enter those pipes and go down into the inlet manifold, which is in the bottom of the sedimentation tank, go through some diffusers, up through the flock filter, up through the plate settlers, and out the outlet manifold and over to the filters. Okay? I am keenly aware that some of this is confusing, like trying to imagine what actually is happening. So you should not be surprised if you're confused. And I have a hard time anticipating how to answer your unspoken question. So if you have a question, don't hesitate. Like maybe you're wondering, why does the water go down at the bottom of the sedimentation tank and then back up? I will show you another view of that. The water is forced down because there are little pipes that it is forced to go in that take it to the very bottom of the sedimentation tank. And then there's a little, what we call a jet reverser that turns it around and sends it back up. So I'll show you another view of that. The inlet manifold and the outlet manifolds are literally just pipes that have either diffusers connected to them, which are little like 1-inch diameter PVC pipes, or little holes drilled in them, orifices where the water enters in the case of the outlet manifold. Another key thing to see in this drawing is there's this exit weir that's right before the outlet channel. And that exit weir is what controls the water level in this tank. And actually that exit weir is the first place where the water does a free fall since the LFOM. So in the linear flow orifice meter, water does a free fall and basically drops into the upstream end of the flocculator. And then there's head loss as it goes down through the flocculator. It enters this inlet channel. It goes through the sedimentation tank or flock filter sed, and then it exits and goes over another weir where there's free fall. And that means that this weir where there's free fall controls the water level all the way back up to the LFOM, to the outlet of the LFOM, or to the very beginning of the flocculator. It means that if you turn the water off, think about this for a second. If I turn the water off to the plant, what determines the level of water in the flocculator? There's no longer any flow. And granted, you have to give it a few minutes for everything to like calm down. And once all the water stops flowing, what level will the water be at in the flocculator? Who wants to be brave? So it's this weir, which is right here under my cursor. That weir is what sets the water level in the sedimentation tank. That will become the water level in this inlet channel, which is the same as the water level exiting the flocculator. And because there's no flow in the flocculator, that will end up being the water level the whole way back up to where the LFOM dumps water into the flocculator, or the very, very beginning of the flocculator. Okay, that was great. So that's this tank and how water flows through it. Here's another view of it, showing what the diffusers, more about what the diffusers look like in the bottom of the sedimentation tank, and showing this idea of a jet reverser where there's a PVC pipe 3 inches in diameter that's cut in half, and that's embedded in the concrete in the bottom of the tank. And the diffusers are literally blowing water into one side of that half pipe, and then the water is going around in a circle and coming out the other side. And the plate settlers in the effluent manifold. So that's another view. Here's yet another view of this same system, showing an end view, an isometric kind of angled view, and a top view. This one is a tiny little 1-inch diameter diffuser. It takes the water from the inlet manifold and forces it to go straight down into, there's a little jet reverser right here. And so the water goes straight down, it exits right here, and then turns around and goes up. And we'll talk more about why that happens. It ends up being a key part of our design. You might also wonder, like, what are these small valves draining? Those are draining the sludge out of the flock hopper. Our questions. That weir that I'm pointing to is how flocks get from the main part of the flock filter sed system into the flock hopper. They flow across that flock hopper, and I'll show a movie of that. And that's what controls the water level of the sed tank. That's that weir that I talked about earlier. And there's a pipe that an operator could potentially drop a light on a string, a submersible light, a flashlight that's submersible, down into the flock hopper and be able to see when the light goes dim as a way to see how deep the sludge is in the flock hopper. So those ports are right here and here, and they line up with the very center or the very lowest part of the flock hopper. Here's some views of workers fabricating these systems, building these systems in Honduras. So they're making the sloped sides, bottom of the sediment, excuse me, of the sedimentation tank. Another view of this flock filter sed. The ledge that you see along the side here is a ledge that will eventually be used to help support the plate settlers. So the plate settlers will be sitting on that, on their edges, on the sides. This platform here is where there will eventually be our system of 4 channels that control the inflow and outflow into this system. And of course, these are the dividing walls between the different units. And you can see the construction here. For those of you who are interested in the structural engineering side, they use a very different way of laying bricks. If you think about bricks, you always want to lay them so that they're overlapped with each other, but you notice here they're not. And the reason is that these are load-bearing walls that have to be waterproof and have to resist significant hydrostatic pressure, because you have to be able to drain one tank while the others are still online. And that means there's the full water pressure pushing on these walls in either direction, depending on which side you drain. And so to accommodate that, there's rebar, and you can see the rebars here. There's rebar that goes right down through between the bricks. So in the mortar, in both directions, both horizontally and vertically, there are rebars embedded, and that's what makes this be a reinforced masonry wall. There also are beams. Sorry, I should know my structures better than that. There are columns, and you can see columns here. These are poured concrete columns in the middle of the wall. I would hesitate to make a case for why that is essential, but that rebar, of course, goes down into the slab below, and that's part of the structural design for making sure these walls are strong enough. And in case it wasn't clear, these in the back are going to be windows eventually in this building. Oh, and you notice brick walls in here, no overlap between bricks. Brick walls out here looks conventional. The bricks are like this. Do you see that difference? Walls that have to hold back water, the bricks are on top of each other so they can run rebar in them. Walls that are just building walls have bricks overlapping and they're not reinforced. See, if I wouldn't have pointed that out, you might not have even noticed that those bricks were different, right? Here they're getting ready to pour the concrete for the slab that will be the bottom of the the 4-channel system that controls the inlet and outlet. These are the couplings, the pipe couplings that will be embedded in the concrete that are the inlet manifold. So they're connected to the inlet manifold. And you can see here I have a second view of this. This is an inlet manifold identical to the ones that you see over here where there's a line of 6 of them. So here's one of those, and that pipe goes down and then comes out at us in the very V at the bottom of the tank. And that pipe will eventually have those diffusers in the bottom of it, pointing the water to the very bottom of the said tank or said flock filter. Okay, they've poured the concrete, so you can see this thing coming together. And you might wonder, like, what are these pipes for? Those pipes are going to eventually carry the settled water, the clarified water, to the filters. And oh, I'm looking, look, there's this guy with the blue hat here. And he's got like a garden hose or some sort of a small water hose. And I'm curious, has anybody seen construction in other parts of the world where you don't actually use a theodolite to do leveling, but instead you use a hose, a water hose? So it turns out this is a pretty accurate way of doing it. That water hose is transparent, so you can see the water inside the hose, and you set the hose up so that there's a little bit of air at the end of each end of the hose, and you can use the water level in that hose. And that water level, of course, is the exact same level on both ends of the U of the hose, no matter where you drag it on your construction site. And so you can use that to mark a level over a relatively long distance. Wow, if that didn't make any sense, I'm sure if you look up water level on YouTube, there'll be somebody that will show you a nice image of that. This is the fabricated inlet manifold upside down with the diffusers pointed up. Those are the diffusers that will be pointed down and will be delivering water into the very bottom, flocculated water into the bottom of the sedimentation tank. And those diffusers are made in a very cool process. And I forget if I have any images of that, but they're made by heating up the PVC in hot vegetable oil on a little stove. And it just needs to go to a temperature a little bit above boiling. It's a little bit above 100 C, and then that's enough to soften the PVC so you can mold it. Here they're making the plate settlers. The plate settlers are made with polycarbonate sheets that are normally used as a transparent roofing material. The sheets are about 1 millimeter in thickness, and then they're spaced apart using a system of pipes. So there's a 1/2-inch PVC pipe that goes the whole way through a bunch of sheets. And then there's a set of 3/4-inch PVC spacers that fit over the 1/2-inch pipe and that create the space between the plates. And there's a view of the finished sedimentation tanks. This is in a single sedimentation tank in a very small plant that doesn't, because it's so small, it doesn't actually have the inlet and outlet channels. It just has a pipe, pipes that send the water into the tank and out again.